Good evening, everyone. Welcome to the April Club meeting for the East Brunswick Astronomy Club. For those who have not yet met me, my name is Isaac Osoris. I'm the president of the club. And welcome. Thank you for coming out. So today, we have a fantastic presentation. This is our typical agenda where we do some welcome remarks. We have a guest presenter, which I will introduce in a moment. We'll open it up for discussion right after. We'll discuss upcoming events for the club. And then, considering conditions do look good, we'll go outside and talk about how do we determine the conditions overview. I'll have my tablet and we'll do a demo of Astrospheric, which is an app that I personally use, and I know a couple of us use it as well, just to check weather conditions, cloud cover, things like that. But then also we'll take a look at Stellarium and see how that's used and know what to expect when we go outside and it's clear. That way we're not expecting Saturn if it's not going to be above the horizon, as an example. All right. So with that, we do have this slide with our mission. I won't read it word for word, but just to recap, all it says is everyone is welcome to our astronomy club meetings. You don't need to be an expert in astronomy at all. We have some folks that have looked through a telescope for the very first time at our meetings, which makes us very, very happy. But on certain nights, we do get great views of Jupiter and Saturn as well. And just seeing the reaction of folks as they look through the telescope, through the eyepiece, and see the rings of Saturn is just absolutely incredible. And that's exactly why we have our club. And just to plug it, just because we don't have many that do take advantage of it, but if you do have a telescope and you are so inclined, by all means, bring it to our club meeting. If the weather's great, you're welcome to use it with us there. If you're having trouble with the telescope itself, we'll do our best to help you as best we can. So we do have that as an option as well, if you are interested. All right. And so without further ado, we do have Dr. Katie Rodriguez-Wimberly as our guest presenter for today. And if her name sounds familiar, she actually did present for the East Brunswick Astronomy Club exactly 1 year ago for the April meeting of 2025, where she presented about ultra-faint dwarf galaxies. But just to remind folks who may have been there, Dr. Katie Rodriguez-Wimberly is an assistant professor of physics and astronomy at CSU San Bernardino, specializing in near-field cosmology and the evolution of ultra-faint dwarf galaxies. She does sit on the Astronomical Society of the Pacific's Board of Directors. She is a first-generation college graduate and Southern California native. And then outside academia, she does enjoy hiking, anime, and adventures with her 2 young children. So without further ado, let's welcome Dr. Katie Rodriguez-Wimberly.
I'm really excited to be back. Thanks for having me again. And to talk about something different this time. So I'm going to tell you all about a type of awesome star called RR Lyrae stars. These ancient stars that vary in the brightness that they put out can illuminate like secrets of our galaxy. They can tell us a little bit about the universe as a whole. So I'm excited to dig in with y'all. Okay, there we go. So why are they called RR Lyrae? That seems like it's a maybe odd name for a whole type of stars. RR Lyrae is actually a star in the Lyra constellation. The way stars and constellations are named, the brightest star in that constellation is the Alpha or Alpha Lyrae, which is actually Vega. We'll talk about that in a moment. And then it just kind of goes down from the Greek alphabet to the English alphabet. And then we start doubling up the letters like AA and BB and finally RR. So RR Lyrae, that star, is actually pretty dim. But it was the first kind of star discovered of this group that's intrinsically variable. And we'll talk about that. But the really amazing thing about this type of star is that it varies, like the brightness changes on this really regular period, which allows us to do all kinds of amazing astronomy with it. But I wanted to dig into Lyrae, the constellation, a little bit, because it is part of the summer triangle. So it'll be up in the sky soon if it's not already up in the sky for y'all. So the summer triangle is what we call an asterism. It is made of three stars, Deneb, Altair, and then Vega, which you can also think of as Alpha Lyrae, the brightest star in the Lyra constellation. In this kind of image here, these stars in the center, that is Lyra, the constellation, and I'll kind of highlight it differently in a moment. So you can see it in the kind of northern sky in the northern hemisphere during our summertime. It rises in about June for me in Los Angeles, but my latitude is 32. Being in New Jersey, no, your latitude is higher. I'm not sure exactly what it is, but you may actually be able to see Lyra already. Lyra is pretty amazing, and Vega is pretty amazing because Vega is the fifth brightest star in the night sky. So in many places around the world, regardless of how dark of night skies you have, you will likely be able to see Vega. And actually, the Earth, as we rotate around the sun, we're tilted on our kind of rotation axis a little bit. And not only are we tilted, but that tilt kind of precesses, as we say. So it wobbles a little bit on that axis. And because of that wobble, Vega will actually become our North Star in 12,000 years. So we have time. But the Northern Star, which right now is Polaris for us, will change because we wobble in that precession. We proceed, which means we're wobbling on our axis a little bit, and because of that wobble, in thousands of years, Vega will actually be the North Star. One other kind of interesting little tidbit that I just wanted to pull out, especially because Lyra will be up in the summer night sky soon, is there is another really amazing star in Lyra. It's called Epsilon Lyrae. So it's one of the brighter ones because it has a Greek name or a Greek letter in its name. This we call the double star. It's not a fantastic cosmic cheeseburger like I wish it was, but it's really interesting. So if you look at Epsilon Lyrae with binoculars, you will see a double star or a binary star. So two stars that are actually orbiting each other, they're pretty close together. And so when you see it with binoculars, you see two stars. But if you look through a telescope with even decent medium kind of magnification, you see a pair of double stars. So each of those binary stars, or the double stars that you see through binoculars, is its own binary set. So these four stars are all orbiting each other. And when they were first discovered, Epsilon Lyrae was thought to be one individual star. And as we keep advancing and creating new technology to stare out into the vast universe, we one day saw that it was two stars and then looked again, and now it's four stars. So amazing things are happening in this tiny little constellation. And the RR Lyrae star is just one of those incredible things happening in this small area of the sky. RR Lyrae, as I kind of mentioned earlier, is pretty dim. So an apparent magnitude, and we'll talk a little bit about this, an apparent magnitude, it's about 7 to 8. And just as a quick point of reference, the more positive a magnitude is, whether we're talking about apparent or absolute, the dimmer it is. So it goes in the opposite direction, which is slightly annoying, but fine. So it's pretty dim because it's about 7 or 8 in apparent magnitude. So I want to kind of highlight what the really amazing thing about these RR Lyrae intrinsic variable stars are. But first, I have to give a little bit of context into how stars evolve in general. So we have this, what we call the HR diagram or the Hertzsprung-Russell diagram. And it's this incredible tool that we keep learning about and how fantastic it is to kind of categorize stars in this way. So, when you go and look through a telescope, you see a star. So you can kind of compare, if you see two stars in your little field of view, you can tell that maybe one is brighter than the other. And you can even sometimes see a little bit of color. Like if you look at Betelgeuse in the night sky, it actually looks kind of red. Vega looks kind of blue. Like you can see slight differences in the color and slight differences in how much light is coming from that star. So you just take those two bits of information, the color, which we can also call the spectral class, and that comes from the temperature of the star, and then the magnitude or the brightness of the star, you can make this incredible diagram that we call the HR diagram. And it has all of these different categories. I've only highlighted 3 here. The main sequence stars are the majority of stars that we see in the night sky. And then we have these giant stars. They are evolved stars, and I'll talk about that in a second. And then I highlighted here white dwarfs. White dwarfs are really, really tiny, very dim. We can't entirely see them very well with even some of just regular telescopes. We need pretty advanced giant telescopes to observe them well. But white dwarfs are what many stars end their lives as. So just to kind of bring us back to the graph before I go into like this wonderful evolution of stars, on this horizontal axis, we're looking at the different types of stars. So you have your O stars, M dwarfs, all of these sort of things. We call these spectral classes. And it's just a way to categorize a star based on their color, which kind of is informed by the surface temperature of that star. And then on that vertical axis, we have absolute magnitude. Absolute magnitude is just a way to kind of talk about how bright that star is if it was 10 parsecs away, which does nothing for anybody, but 10 parsecs is 3.26 light years away. And a light year is how long it takes light to travel in 1 year. So light from a star that is 3 light years away takes 3 years to get to us. And so this kind of goes into that idea that when we look out in the night sky, we're not only looking out far in distance, we're also looking far back in time because light has had to leave those stars and then get to us. And that it's not only crossing distance, but it's crossing time. So we can categorize all of the stars in the night sky in this way on this one diagram. But what we can also do is look at how stars evolve, because as stars are born, they're kind of born in these weird amorphous areas that are not really well understood yet. These are called protostars. I'm going to talk through kind of our sun's evolutionary path and then talk a little bit about our Lyrae stars. But as stars are formed in clouds and gas and dust, we call them protostars. And then they fall onto that main sequence of stars. And you can see where our sun is on that main sequence. If I just back up a little bit, we are a kind of FG type star. Our absolute magnitude is just about 5. So our sun, and you can see it from kind of highlighting it on here. Well, that's fine. Highlighting it on here is kind of a normal type star. So as these medium mass stars live most of their lives in this, what we call main sequence, they're creating hydrogen in their core, helium in their cores from hydrogen. And at some point they stop creating helium in their cores. They essentially run out of fuel and they literally puff up, like the star gets more massive. That's why we call it a giant star. So it gets more and more massive, and as it grows and grows, it can't sustain that anymore, and so it shrinks down and becomes a white dwarf, which we just saw at the end of that little animation. So that's what's going to happen to our sun. Our sun is fairly young age, so you and I don't have to worry about it. Our grandchildren, great-grandchildren don't have to worry about it. It's like hundreds of thousands of years from now. But at some point, our sun will grow, and the radius of our sun will encompass Mercury, maybe even Earth. We're still trying to figure out how big the Earth will get, how big the sun will get as it's starting to die. And then when it does die, it'll shrink down into being a white dwarf and fairly dim at that point. So every type of star on this main sequence has some kind of evolutionary path where it starts to expand as it runs out of fuel to create helium out of hydrogen in its core. And then it grows, it becomes a giant star, and some of them go off supernova and become black holes. Some of them just kind of fade into white dwarfs. And then there's other stars that live for a while in what we call the instability strip. So these stars that are just off of the main sequence, they've just stopped burning hydrogen into helium in their cores, and they're physically pulsating as they start to die, essentially. So we're seeing kind of the last stages of a star when we're looking at these RR Lyrae stars. So to kind of bring that all together, this type of star, it was first found in the Lyrae constellation. All of them have about the same mass. So they're less massive than the sun, about half the mass of our own sun. They're all old, so they're all about 9 to 10 billion years old. And for a bit of context, the universe, we think, is about 13.8 billion years old. So these are some of the first stars that were ever formed. And now we're kind of getting a peek into their end stages of life. They're also intrinsically variable, and I'm going to talk more about that in a second. And we'll dive into their periods, but that relates to how long it takes them to expand and contract. And the incredible thing is that with RR Lyrae stars, it takes less than a day for this entire star, this thing that is half the mass of our sun, to expand and contract in less than 24 hours. These stars were first discovered in the mid-1890s, so over 100 years ago. Because they're so old, they don't have a lot of stuff in them. In astronomy, we like to say that anything that is not hydrogen or helium is a metal. So carbon, oxygen that we breathe, astronomers call it a metal. We get a little wild with our naming conventions, but our Lyrae stars are metal poor, which just means they don't have a large variety of elements or stuff inside of them. Because they're old, we call them population 2 stars. So they're this kind of middle generation of stars that was born within the universe, but they're like the elder millennials of stars. So they're on the older end of this population 2 stars. And while we learned about them in the 1800s, it actually wasn't until late 1900s, so about 100 years, that we finally saw this type of variable star outside of our own galaxy, the Milky Way. So we continue to learn about them almost every single year. We're learning new things about this incredible type of star. So what do I mean by intrinsically variable? It literally means that the star itself is changing And through that change, we see it as a change in how much light is put out by the star. So I think this is a wonderful example. Betelgeuse or Betelgeuse, which is another very bright star in the night sky in Orion, it is at the end, kind of near the end of its lifespan also. At some point, it is going to go supernova. And so if we stare, we've been astronomers and, space lovers all over the world have been staring at Betelgeuse for a long time. And so if you, with the VLT sphere, the Very Large Telescope. We took a picture of it in January, not we, some other amazing astronomers took a picture of it in January 2019, and it looks like that. And not even a year later, you take the same picture and it physically looks different. That means it's intrinsically variable. The amount of light coming from January is more than the amount of light Betelgeuse was putting off in December. That means it's intrinsically variable. The star itself is changing its shape, which puts off its different amount of lights. In Betelgeuse's case, it will go supernova at some point. With RR Lyrae stars, many of them are not quite as massive to go supernova, so they'll kind of continue to expand and then fall down, shrink down once and for all and become a white dwarf. So with RR Lyrae stars, they're literally like the stars, the outer layers. So once the star stops burning hydrogen into helium in its core, it starts to compress because there's not a lot of energy being pushed outwards from the core because you don't have nuclear fusion going on anymore inside of the star. So those outer layers start to compress because gravity starts winning. There's no pressure pushing out, so gravity starts winning. As everything is collapsing down, the temperature increases in the star. As the temperature increases, more electrons and little tiny parts of atoms within those outer layers move around quicker and actually trap all of that new heat as everything is falling down. When it gets too hot, then you do create pressure. So it's not nuclear fusion pressure, it's pressure from this kind of collapsing or compressing. And so the pressure starts to win and the star starts to expand. So those outer layers actually start moving further away from the core of the star. And as you can assume, as it's moving further away, the temperature decreases because there's less stuff everywhere, or the stuff is more spread out. So it decreases and the temperature decreases to a point that then gravity wins. So it's really this like tug of war between gravity pulling things inward and pressure from all of the stuff that the star is made up of, pushing things outwards. And in intrinsically variable stars that repeat their variability, this happens like with RR Lyrae stars. It literally happens in less than a day, that it expands and contracts in less than 24 hours, which is a wild amount of physics happening, an entire star expanding and contracting all the way down in less than 24 hours. So we can look at these stars individually. We've been doing this for over 100 years now. And I wanted to share this different kind of version of looking at how the star is changing its brightness over, we'll look at 600 days of different RR Lyrae stars changing their variability. But through something that is run out of the Center for Astrophysics at Harvard and the Smithsonian, it's called Sensing the Dynamic Universe. We're so used to looking at the night sky and just visualizing it. But if we put sound to these kind of visualizations, it lets us experience the universe in a whole different way. So hopefully the sound works. Let's give it a try. Yes. So the higher the pitch here, the brighter the star is on that observation. The lower pitches, it's lower. At during this kind of quiet period, the star was not visible in the night sky. Remember, this is over about a 2-year span. And so we can put notes to every one of these observations and listen to the universe. And so here we're just looking at the days. This modified Julian day is just a way to kind of put all astronomy observations on the same scale or on the same calendar. You can think of it like that. And then it was looking at the magnitude or the brightness of the star. We can look at this in a different way also, where instead of just looking at the days when we are observing that star, we can think about the period. So, how long is it taking to go from expanded and very dim to contracted and very bright? This star in particular is doing that in just 9 hours. So, one period of the star is just 9 hours. And we can hear it in this new way. So this is literally like a cosmic scale, right? Going from high pitch, which is showing us bright, um, the how bright the star gets, all the way down to lower pitches, which is how dim it can get, and it just flows through that pattern for thousands of years as it's kind of evolving towards the end of its life. But you can see all of the dots, all of the notes that we heard in the previous video are in this video as well. But instead of just kind of randomly looking at different nights, we've reorganized it to put each observation into the phase of the stars. So one full phase goes from peak brightness to dimness back to peak brightness, and that happens in just 9.2 hours for this star. So if you are, just put a quick plug in for it because I love the Sensing the Dynamic Universe program. If you just search that or look for it through the Harvard websites, there's all kinds of incredible astronomy space visualizations where they've taken this idea of connecting visual cues with audio cues, and you can experience our universe in a whole other kind of sense regime, which is really, really fun. What's also amazing, back to RR Lyrae stars, what's really interesting about them is the vast majority of them we actually see in something called globular clusters. Globular clusters are like these beautiful diamonds in the sky. They're really, really bright, many of them. Here's an example of 3 of them. Something like Messier 15 here in the bottom left, which was this picture was taken by the Hubble Space Telescope. There's just thousands of stars packed into this one little area. All globular clusters, regardless of the number of stars in them, were formed all at the same time. And one thing about stars is the kind of mass of the star, once it is a fully formed star, dictates how long it's going to live. So the really massive, bright blue stars that are very young, they're not going to live a very long time. They kind of like live fast, die young in a sense. So they'll be on that main sequence of the figure we were looking at earlier. for a while, cosmically speaking, but then fairly in a short lifespan for stars, they will go supernova, and some of them will become black holes, some will become neutron stars, all of these really amazing, wild things out in the universe. That happens in globular clusters. And then some of the stars, if a star is born and it's very small, it's really easy to be small in the universe. You don't need a lot of energy, you don't need a lot of stuff. You just kind of roll along as a tiny little dwarf star. Dwarf stars, as they die, still evolve or still expand a little bit, but they fairly quickly become the white dwarfs that we saw on our HR diagram. And what's neat is that in globular clusters, all of the stars were born at the same time. But because the mass of the star dictates how long it's going to live, after, millions and billions of years, we end up seeing globular clusters as these really dynamic groups of stars where there's little red dwarf stars. There's a ton of them throughout these systems. Then you have still some of the brighter, bluer stars that are starting to die. Sometimes they're supernova. And we see a lot of these RR Lyrae stars within globular clusters. And what's great about globular clusters is we see a ton of them in the stellar halo of our own galaxy, the Milky Way. So we'll pause on stars for a minute to talk about galaxies, my favorite things, but specifically to talk about the Milky Way. So we think our galaxy is a spiral or a barred spiral galaxy. So you can see the little bit of like extended bar shape there in the middle. We have a black hole in the center of our galaxy. It's an incredible thing. Sagittarius A star, it's named. Maybe not the most creative, but still exciting. And then there's literally arms of gas and dust extending from that center, orbiting around the black hole. And our solar system, our star, the sun, is here about 2/3 of the way out into one of the arms. This kind of image here, this flat circle, we literally call it the disk of the galaxy, where the spiral arms and most of the gas and dust exist within our galaxy. We have a thin disk and a thick disk and a galactic bulge. And then, so there's, this kind of like weird flat anatomy to our galaxy. But that disk, the bulge and everything, live within what we call the stellar halo. This thing is massive. It is 300,000 light years across. So the diameter of the stellar halo is much bigger than the disk of our own galaxy, which is just about 100,000 light years. So light from the stars, the RR Lyrae stars that we're seeing in those globular clusters that are in our stellar halo, may take about 150,000 years, or sometimes more if they're coming from the opposite side of the stellar halo, just to reach us. And then the last little bit of galactic anatomy that I want to point out is we think every galaxy lives within its own dark matter halo, which just means it's a giant ball of dark matter that's kind of housing and protecting us from all of the other environment that's going on in the universe as a whole. But this stellar halo, just one other view of it, it kind of expands around. It's like its own sphere of stars and globular clusters. Because it's far away, even though it's within our own galaxy, it's hard to really study it. But globular clusters, because they're really only in our stellar halo, not so much our disk, give us this incredible insight into the shape of our own galaxy. And now that we can see these globular clusters and RR Lyrae stars in other nearby galaxies, we can learn about their stellar halos. And it's allowing us to put together this better picture of what galaxies are and when they were formed and how they were formed, because we know the RR Lyrae stars are about 10 billion years old, and the universe is only about 13.8 billion years old. So we're getting clues into how galaxies formed by studying this one special type of star. What makes these kinds of stars really special is what we call technically the period luminosity relation. Really what that is that if we we study a whole ton of RR Lyrae stars and other type of intrinsically variable stars like Cepheids, there's different types of Cepheid stars, and we look at how long it takes them to go through that compression, expansion, compression cycle. That's its period, and how its brightness or how much light it puts off during that cycle, how that changes over the cycle. We can look at the luminosity or how bright the star is and that period, and it has this really nice relationship. Every RR Lyrae star we've ever observed, and every Cepheid variable stars, which there's a ton of them that we've ever observed, they fall on this beautiful relationship. This allows us to take things that we can observe, like the apparent magnitude and its phase, and connect it to periods and the luminosity or the apparent brightness, the absolute brightness. So how bright the star would be if it was about 3 light years away. So we can compare this left graph here we call a light curve. It's just showing us how much light is put off throughout this different part of the cycle. Compare that to this well-known period luminosity relationship that allows us to figure out both how bright we see the star in the night sky and how bright the star would be if it was 3 light years away. And there's a relationship there, right, between how bright something is where we see it and how bright it is 3 light years away. That allows us to use all of those kind of pieces of information to actually find the distance to every single one of these variable stars. We call this a standard candle. So it allows us to peer out into the night sky and kind of piece together how big our galaxy is, how far away other galaxies are. And all of this work was pioneered in the very early 1900s by Henrietta Swan Leavitt. She was, you may have heard of Harvard's calculators. She was one of these calculators that by hand observed thousands of variable stars and painstakingly calculated their phases and their absolute magnitudes and their apparent magnitudes and put together this relationship, which now is allowing us to learn about how giant the universe is. And this kind of all comes together in something we call the cosmic distance ladder. So we know the universe is just almost unfathomably, unknowingly large. But we want to try to figure out, okay, but how large is really large? And we can do that by piecing together how far away everything is. Our Lyrae stars, this kind of red curve here, will take us out to about 2 million light years away. So we can use parallax, which is just kind of the angle of the stars. If you're looking at it on, in different periods of our orbit. So like in January and June, you can see an angle between those stars. That's parallax. We can use parallax and some of the more nearby RR Lyrae stars to really calibrate or refine that relationship. And then now that we see our Lyrae stars in other galaxies like the Andromeda Galaxy or M31, we can extend that part of our distance ladder to get really good measurements of how far away our nearest large galaxy is, which is M31. And we can continue to use stars in these different ways to kind of hopscotch from things within distances and stars within our own galaxy and our own kind of solar neighborhood out to our closest neighbors, further out to groups of galaxies, and one day even going out to, 11 billion light years away to the nearest cluster of galaxies, which are these giant groups of like 1,000 or more galaxies all kind of crammed together in a very, very busy area of the universe. And so we want to figure out how far away everything is, which again is allowing us to look further back in time. And distances is really important in all of that, but we have to continually refine the foundation of our ladder so that we can build out further and further with the more advanced technology that we have. So this is why I really am excited to dig into our Lyrae stars, because while it's something that we've been staring at for over 100 years, we're still learning more and more information about them and using them to really refine our models of how big the universe is and where our own galaxy came from. What is difficult about this, and part of the reason that it's taking hundreds of years to figure it out, is that even though it's great that the stars expand and contract in this very regular period, the star is constantly moving, right? And that makes it really difficult for us to measure how fast it's moving, because not only is the star moving towards us or away from us and kind of side to side in the night sky, it's also oscillating as it's doing all of that motion. So there's a lot happening, which means we really have to study many of these stars to put together that relationship and do something we call calibrating the errors, or making sure the full range of what the velocities might be or the speed of the star might be is incorporated with that oscillation of the surface of the star. And so just to kind of, again, highlight what these light curves look like, we can either look at them in the magnitude, so how bright the star is over its phase. This is a different, still an RR Lyrae star, but it has a little bit different of a curve than we saw earlier. So it'll go from dim to bright to dim in one phase or one period. And its radial velocity will also go from low to high to low in the same period. So the rate that radial velocity of the star changes exactly follows how bright the star is, which is great. But as you can kind of see from this graph, or these two graphs, this is looking at 5 different RR Lyrae stars, hundreds of observations, and it takes that much information to start to piece together how these relationships work together and how we can use this changing speed to actually have good measurements of how far away that star is. But this is where advances in technology are kind of saving the day, and like big data in a sense. So all of this work, finally talking about the work that I'm doing now, all of this work is really led by my undergraduates at California State University, San Bernardino. There's my group there from a summer ago. And they're using data from the Sloan Digital Sky Survey. That's this SDS. This is an incredible telescope in Chile that has been just observing the night sky night after night after night. Every time there's no clouds, it looks out in the night sky, and it's been doing that for over 20 years. And so with SDSS, they have mapped over 50,000 RR Lyrae stars in the night sky through something called the Milky Way mapper. And they're just, again, just everything that we can see. We're trying to look at it. This image here, the kind of green line through the center, that is the disk of our Milky Way. So it's looking out into the edges of our Milky Way. And then you can see some bright spots or some darker spots in this image. Those are all those globular clusters which have RR Lyrae stars in it. We compare this data, which is looking night after night at just millions of stars, with an incredible telescope that just ended its mission a year or so ago called the Gaia Space Telescope from the European Space Agency, ESA. This incredible space telescope found really detailed positions and velocities for 1 billion stars in and around the Milky Way. Literally 1 billion stars. And it did this in just 5 years, which is wild that we could get that much information in a very short amount of time. And what Gaia's real expertise is looking at something called proper motion. So if we think of a star in relation to our sun, it has some distance out to it. The radial velocity is how fast that star is moving away from us or towards us. And then there's something called the transverse velocity. And so that's kind of how fast it's moving left or right on our night sky. That transverse velocity you can actually measure as something we call proper motion. These proper motions are incredibly small. So for 1 billion stars in the night sky, we now have this incredibly small measurement of how fast that star is moving left to right on the night sky, which allows us to get the full kind of 3D or space velocity for all of these stars and kind of pull out the distances to all of these stars. So we can take individual measurements from Gaia and compare them to a handful or a number of measurements from SDSS and really put together the largest calibrated data set of RR Lyrae stars that has ever existed. And my students started doing this. They did this for 2,500 stars over one summer, and they're continuing to work to get up to that 50,000 star range. We're learning a lot of data, big data analysis to get there. And what's nice, and this plot kind of looks like a mess, but I'm actually really excited about it because it's showing us that we have this kind of full range of radial velocities, which is here on the horizontal. We have a full range of observations throughout the period or the radial velocity phase of that star. And the amplitude, which kind of shows what the height, what the greatest part of the radial velocity is, we also have a range in that. So we're getting to look at all possible RR Lyrae stars in the night sky and really piece together a lovely light curve and information about these stars that will be the largest data set for this particular type of star that has ever existed. So what we're currently doing right now, just to kind of bring in that little bit of detail, is really trying to calibrate those errors. And I can show real quick, if I go back here, the errors is like, if you look at this magnitude versus phase graph, there's gets a little fat down there, right? Those observations are spread out. The width or the height of that line is actually the error. So what we want is like one magnitude or one radial velocity for every point in the phase, and then a small range of what that can be. And that'll allow us to really find the distance within a nice range, but we know it's accurate in that small area. So with these 2,500 RR Lyrae stars, that kind of span the whole range of possibilities for both observation period and radial velocity. We can really calibrate those errors and give a what we call a 0 point, or this is what the radial velocity is, kind of on average as the star is expanding and contracting. And what I will use this for is really my favorite part in this kind of idea of near field cosmology, or learning more about how the universe came to be by studying things that are nearby us. Once we have this calibrated 50,000 star deep catalog of RR velocities, we can go and look for new stellar streams in our stellar halo. Stellar streams kind of give us this peek into how our own galaxy, the Milky Way, was formed. These we didn't really start discovering until maybe 15 or so years ago, as again, technology just developed and we got more tools to process large sets of data. This allowed us, what we can see when we have really good velocity measurements and distance measurements, is that the Milky Way has kind of absorbed a lot of small galaxies. Many of these stellar streams are actually small galaxies that were ripped apart as they got too close to the Milky Way and just kind of became part of our own galaxy. So the Milky Way, just like the USA is a big, beautiful melting pot, the Milky Way is a big, beautiful melting pot of many smaller galaxies, and we can see these in the stellar streams. And we can also use the RR Lyrae to actually measure the mass of the Milky Way, which seems to be changing much more than we thought it was as we kind of collect new galaxies. But using the speed and gravity that we can see within our own galaxy, we can figure out how massive our galaxy is, at least within 10,000 light years, which is pretty far out in the universe. And then it allows us to compare ourselves to other galaxies that we observe that we can't see our Lyrae stars in because they are too far away. So that is all I have for you. I'm very excited to take questions and actually be able to chat now.
Yes, thank you very much for a very edifying lecture. My question for you is: before the discovery of these RR Lyrae celestial objects, what could be? I'm still trying to get an idea of exactly what they are and how we're using them. Can you give us another example of of a celestial object that was similar to these RR Lyrae stars that we were using to do a lot of these things that you're saying that we're using the RR Lyrae stars now to figure out the distance of certain objects, of the age of of our universe and our galaxy, things like that. What were we using before to help us with this kind of calibration?
That's fantastic. So, interestingly, so before, the first things that we were really trying to use to understand distances in the universe are supernova. So when a star, very, very old, massive star, literally explodes, there are some supernova that are so bright you can actually see them in the daytime, and we have record of this in like 10,000 CE AD. There was across the northern hemisphere in ancient Chinese records, in I believe ancient like Roman records, you saw everyone writing about this star in the daytime, which we now know was a supernova. So supernovas are really, really bright. And because of that brightness, you can see further back in space and time than normal without, our advanced technology. But supernovas actually are very, very quick. The actual explosion generally takes less than 1 minute. It stays in, like, if it was so bright you could see it in the daytime, you could see it for maybe a couple of days, but that's not very long at all. So there was some work trying to do that. There was also groups of people looking at like globular clusters or what we call nebula. So like really bright clouds of gas and dust where there's new stars starting to form. So they're very, very bright because they're dense with a lot of gas. And you have the kind of baby star inside of it that's starting to put light out, and that light bounces around in the cloud. So it kind of intensifies how bright the light is. And at this same time, so in the early 1900s, we didn't know whether our own galaxy, the Milky Way, was the entire universe or just one of many galaxies. And studying RR Lyrae stars and Cepheid stars, so these stars that literally expand and contract, was one of the things that helped astronomers realize that the Milky Way is just one of kind of a countless number of galaxies inside of the universe and not us at the center of everything. Does that help kind of give some context?
Yeah.
Awesome.
Yes.
Fantastic.
You have a question?
Hi, it was a fantastic session.
Thank you.
My question is, how do you know when a star is born, if it's a new star, and how do you start monitoring it? And how do you know that's going to be one of these categories of stars? Like,
Yeah, that's a fantastic question. So actually, it wasn't until like 2 or 3 years ago when we finally, for the first time, got a picture of what we call a protostar. So a lot of the way, because cosmic scales take a really long time. Even our massive stars that die fairly quickly, that's fairly quickly in the terms of billions of years, which we won't ever be able to observe like with our own eyes. So we get pictures of the night sky. And what we do is compare that to simulations. So we create these like essentially virtual universes using math and like the laws of physics. We put that into a program and say, go, like let time run and see what happens as all of these physical laws dictate what we think should happen in the universe. And then we compare those simulations to observations. So our theories that within these clouds of gas and dust, stars can start to form because it gets dense enough that gravity starts to pull it together and hot enough. And once everything is dense enough and hot enough that that hydrogen can combine and start to create helium, that is nuclear fusion. And that is what is at the center of stars. And so everything just kind of condenses in that cloud into a star. So we started by kind of just plotting what we see in the night sky on that diagram where we're looking at the color of the star and the brightness of the star. And it wasn't until that was done over 100 years ago, and it wasn't until the recent decades where we started to realize that, when stars are formed, they're these baby stars or protostars. They have different kind of brightnesses, and we're still really learning where those go on that HR diagram, but that the majority of the stars spend their lives on that main sequence, and then they expand into a giant, and then they either explode or just kind of dwindle down into a white dwarf. So we had these tools to categorize the stars but it wasn't until we really started being able to compare them to our theories through like models and simulations that we pieced together how they evolved.
So we do have a question in the chat.
Awesome.
Is it preferable to work with one scope for a long period of time, or as they become available, use newer, better telescope models?
Oh, that's a fantastic question. I think it really depends on one, the goal of your study. We don't always need like the largest, most advanced telescope. Sometimes you just need to stare at a thing long enough to get information on it. And actually, there's an organization called the AAVSO, the American Association of Variable Star Observers. And this is a group of what we would call amateur astronomers, but just folks that love the night sky and have like, backyard telescopes. And they study a lot of these RR Lyrae stars, but the Cepheid stars as well, and put together a lot of this information that's helped us calibrate those relationships. And so now that we really, as a community, believe in that relationship, we can go out and use the more advanced telescopes like Gaia or the Sloan Digital Sky Survey to do what they have done on, tens of stars for tens of thousands of stars. So it really takes all ranges of technology and telescopes to understand the full story of any kind of thing out in the universe.
Thank you. That's
Yeah.
pretty awesome, because I was wondering if there was a sort of citizen scientist thing around this, and you answered that. So thank you.
Yes, you're welcome. You're welcome.
Yeah. Thank you so much for a very interesting talk on this subject.
Thank
It's
you.
worth about several PhDs, I believe. Yeah, so much information.
Thank
The
you.
question I have is this: RR class of stars,
Mhm.
or doubles or whatever, not now, number of stars. Do they have this kind of phase, short phase? Actually, we are talking about 1 day, 1 Earth day, right?
Yes.
Oh, why is that so short? All of them have the same phase of one day or close to that?
Yes, all of the R. I mean, so I guess I can expand it a little bit. And if I go to this image, nope, this one. Sorry. Okay, if we go here, the RR Lyrae stars, any star that is intrinsically variable, that does it for years, with a regular period. If the period of expansion, contraction, and back out to expansion is less than a day, then we call it an RR Lyrae star. If that period is a day or greater, then it's a Cepheid variable. So Cepheid, Delta Cephei was just the first of those more massive intrinsic variable stars that takes longer, about 10 days to go through one period. RR Lyrae was the first of that kind of star. So the naming is just based on the first of the star that we saw it. But these stars they pulsate faster because they're smaller, and so they can. Cepheid stars are actually more massive. Most RR Lyrae stars are all about half as massive as our sun. Our Cepheid stars range from as massive as our sun to much more. I don't know the top range, but much more massive than our sun. And so it takes them a little bit longer to go through one oscillation period.
I was wondering, like, with these Lyrae stars, since they are quite old, what can it tell us in like relation to like cosmology or even the age of our galaxy? What can it tell us about the past, and what can it tell us about like the future?
Yeah, that's a fantastic question. So because most of these, yes, they're mostly about 10 billion years old, and we see them in these globular clusters and then in these streams of stars. It's kind of showing us that the galaxy has been forming for a very long time. So our galaxy, or at least smaller galaxies that kind of smashed together to form the Milky Way, has been around for a long time. And that really helps us piece together what the early universe looks like. Even with our most advanced telescopes, like the James Webb Space Telescope, we still can't see the very first stars or galaxies that were ever formed. If you've heard of JWST's little red dots, we think those are something like the first galaxies, but literally the pictures of them are like a little red dot, so we don't get much detail. But these stars, because they've existed over the past 10 billion years, we can kind of track their velocities and start to piece together what environments they were formed in based on what they're doing today and really what elements are inside of them. Because we know where every element is formed in the universe or how it's formed. Many of them are formed when the massive stars go supernova. We can kind of piece together their evolutionary history based on what's inside of them and their ages. So we can get good distances and then take those distances to start to piece together the history of that star or that globular cluster. And if you kind of push the clock forward instead of winding it backwards, we can measure out, like, these are our Lyrae stars and Cepheid variables. They are no longer forming hydrogen into helium in their cores, which means at some point they're going to get massive enough, their period will slow down, that they'll just collapse into a white dwarf, or if they're massive enough, they'll actually go supernova. And so we can look at what might happen to our night sky as these things actually start to die or fade to a point where we can't see them with an unaided eye.
One more in the chat. It says, just to clarify, meteor showers are named based on apparent origin. Are Lyrae or Cepheid stars that are being discussed named similarly, where you are looking within those specific constellations?
Yeah, so almost. The first RR Lyrae star is in the constellation Lyrae. Any other Lyrae, RR Lyrae star just acts like that first one that was found. And same with Cepheids. Delta type 1 Cepheids, which we call Delta Cepheids or Delta Cephei, are all act very similar to the first of that star, which was found in the Cepheus, in the Cepheus constellation. So kind of the same, but only for the first star that was found, not the entire group, if that makes sense.
So thank you for a wonderful presentation. I kind of took away from that this phenomenon is largely produced as stars age, and the balance between the energy output from fusion kind of butts up against the internal gravitational forces pulling them in together. And it's kind of a product of the shift in that balance. You mentioned later on in the presentation that we've observed galaxies being absorbed, crashing into each other. Since that can happen, it stands to reasons that stars eventually could mesh together and merge. Would a shift like two stars colliding produce enough of a shift in their internal balance to produce a similar phenomena? And what could we maybe learn from observing something like that?
Yeah, that's a fantastic question. And it does happen. And actually with these double stars or binary stars, if they are aligned in such a way that like one passes in front of us or between us and the other one, and they kind of orbit like that, we will see those stars, their brightness change also. And so some binary stars will get so close together or have such a strong pull that they will merge into one. And we see that as in the night sky, we see that as changing luminosity. So as they get closer together, they're speeding up because gravity is really kind of pulling them in. And so this same process of gravity condensing them into one, and so their brightness increases because they're getting more tightly packed. And then after that, they get too tightly packed, and then kind of the pressure on the inside increases, and so they expand a little bit, which dims them. And that can happen as well as it kind of settles into whatever its possible like equilibrium state is going to be. We haven't actually captured younger binary stars falling in and kind of merging together. We have seen this through gravitational waves with something called neutron stars. And these are very, very old stars. They're really small and very, very dense. And so they have a lot of gravity. And if they are in pairs of stars, a double star, those will fall in and merge from two neutron stars into one neutron star. And that is so powerful that we've actually collected the gravitational waves, or the kind of waves and bends in space and time, because of those two massive things colliding. So we've seen it on the really, really extreme end. Theoretically, it should happen in this more common type of star. I just don't know if we have a great observational data set for that yet, though.
Last call for questions. All right, not seeing any. I will take this opportunity to thank you, Dr. Rodriguez-Wimberly, again for joining our club for the second time. So thank you so much for your time.
Yes, thank you so much for having me. Again, fantastic questions. It's a pleasure to visit.
And then just really quickly, UAC, NJ, and EB Astro upcoming events. Every Saturday, UAC NJ at Jenny Jump State Forest has free public programming. The next one on the 18th is Astronomy for Beginners. The 25th to be announced based on their website. And the first one of the month is typically What's Up in the Month Sky. So that's for the 2nd of May. And then the 9th, The Life and Legacy of Charles Messier. With regards to EB astronomy events, we have our next meeting on May 21st. Please take note of the time. Because this is our seasonal kids meeting, it will be earlier. It's at 6:30 in the evening. But then in June, we'll switch back to our 7:30 time slot. But for this one, it's about satellites, space probes, and more. And we'll have Kevin, who was here earlier, give a presentation on things that we've sent up into space. And then we have an activity to make a lander, and hopefully our eggs survive the trip. So be sure to come out for that. Our kids meeting are very highly attended, and they're a lot of fun, especially with the demos. So really quick plug, just because we're short on time, we have our quickfire presentations. If anyone was here for our August 2025 meeting, we did sort of this thing where we called it quickfire presentations. We invited you guys, instead of sitting there, you would come here and give a quick talk, 5 minutes tops, about whatever astronomy related topic that interests you. So if you wanted to talk about maybe a couple years ago, around this time actually, when we had the solar eclipse and what that experience was like for you, you can chat about it. And you're in a group of folks that are inclined in the similar topics. So it's a safe space to just have a nice conversation about astronomy, but then giving you the opportunity to be up here instead of me, which I like a lot. But we're trying to rename this. Quickfire presentations is great, but it would be awesome to have something astronomy related, catchy, fun. And we're going to make it a contest for everyone. So if you have any suggestions, let us know. But more to come on that, and how to submit proposed names and things like that to come. Yeah, instead of quick fire, name it, what is it, Meteor Minute Talks or something like that, something space related, something fun. And we'll come up with a nice prize for everybody. And the best way to stay in touch is Facebook, that QR code, or Instagram, that one. But if you have neither or are not inclined on those, by all means, sign our sign-in sheet. You can leave your email and we'll reach out to you. Let's go outside.